Imagine looking into the night sky and realizing that somewhere out there might be another Earth with oceans, mountains, and maybe even life. Could Earth-like planets really exist? In this video, we'll explore Earth-like planets, how scientists find them, what makes a planet habitable, and the biggest discoveries so far. When we talk about Earth-like planets, the first question that arises is, what exactly do we mean by Earth-like? At first glance, one might assume it refers to any planet that looks similar to Earth, perhaps with blue oceans, green continents, and a breathable atmosphere. However, in astronomy and planetary science, the definition is more careful, rooted in measurable characteristics that can be compared to our own world. An Earth-like planet is not merely one that appears familiar, but rather one that shares several fundamental qualities with Earth: size, composition, orbit, and potential habitability. Size is the most straightforward characteristic. Earth is classified as a rocky, terrestrial planet, distinct from gas giants like Jupiter or ice giants like Neptune. So, for a planet to be considered Earth-like, it must be within a certain range of Earth's size and mass. Too small, and the planet cannot hold onto an atmosphere, it will leak gases into space over time, like Mars has done. Too large, and it risks becoming more like a mini Neptune, with thick, suffocating layers of gas and no solid surface to stand on. Scientists generally consider Earth-like planets to be those ranging from about half Earth's size to no more than twice Earth's size. Within that range, gravity should be strong enough to retain an atmosphere, but not so overwhelming that it crushes. The possibility of a surface environment. Composition is the second critical element. A world made mostly of gas or ice, even if it were Earth-sized, would not truly be comparable to our home. Earth-like planets are expected to have a rocky composition, with iron, silicon, magnesium, and oxygen dominating their structure. This rocky nature provides the possibility of solid surfaces where liquid water might pool, where mountains and valleys might form, and where life as we know it could find a foothold. Without a rocky surface, the notion of an Earth-like environment becomes tenuous. Orbit, however, is where the definition becomes more nuanced. A planet may be the right size and the right composition, but if it is orbiting too close to its star, its surface will be scorched and inhospitable. Much like Venus, if it orbits too far, it will be a frozen wasteland like Pluto. So, the term Earth-like is often tied to a planet's location in its star's so-called habitable zone, the region where conditions are potentially just right for liquid water to exist. Earth is, of course, the prime example of this balance, but other stars, especially those smaller or larger than the Sun, have habitable zones at very different distances, requiring astronomers to carefully measure orbits to decide whether a candidate is Earth-like. It's important to remember that Earth-like does not automatically mean Earth twin. In fact, no discovered exoplanet has yet been proven to be an exact twin of Earth in every respect. When scientists classify something as Earth-like, they are often highlighting that the planet shares enough of the key factors: size, composition, orbit that it warrants further study. It's a way of saying this world might resemble Earth in some meaningful ways, and therefore, it might hold the potential for life. The word potential is crucial here. There's also a broader perspective to consider. Our definition of Earth-like is biased by the fact that Earth is the only known planet with life. We assume life needs conditions like ours: a rocky world, moderate temperatures, liquid water, and an atmosphere that contains gases like oxygen, nitrogen, and carbon dioxide. Yet, life might be possible under very different conditions. By focusing on Earth-like planets, scientists are prioritizing the most familiar path for life, but it does not mean these are the only possible havens for biology. When astronomers search for exoplanets using telescopes, the idea of Earth-like serves as a guiding filter. The sheer number of planets in the universe is overwhelming, billions upon billions. In our galaxy alone, many of these are gas giants, others are icy dwarfs, and countless more orbit outside the habitable zones of their stars. But when the criteria of Earth-like are applied, the list narrows to a more manageable and fascinating subset. These are the worlds that might, in the distant future, be targeted for interstellar missions, robotic probes, or at least intense observation with advanced telescopes. One fascinating implication of this definition is the way it reshapes our place in the universe. For most of human history, Earth was seen as unique, a singular oasis in a vast and empty cosmos. The discovery of Earth-like planets, however, has shifted this perception dramatically. Suddenly, we can point to worlds dozens, hundreds, or even thousands of light years away and say, this planet is about the size of Earth. It orbits in a habitable zone, and it might, just might, be a home for life. This realization inspires both awe and humility, as it suggests that our planet, while special to us, may not be so unique in the grand scale of the universe. Of course, Earth-like is still a rough classification, without direct observations of surfaces, atmospheres, and climates. Astronomers can only infer so much. A planet may check all the boxes: size, orbit, composition, but still turn out to be barren. Venus is the ultimate cautionary tale in this regard. Roughly the same size as Earth, located not far outside the Sun's habitable zone, Venus might seem Earth-like from afar, yet its thick atmosphere of carbon dioxide and runaway greenhouse effect make it a hellish world of crushing pressure and searing heat. From this perspective, the definition of Earth-like remains provisional, a starting point rather than a guarantee. Nevertheless, the term carries enormous weight in both science and imagination. Each announcement of a new Earth-like discovery sparks headlines, fuels discussions about extraterrestrial life, and captures the public's imagination about colonization and exploration. It is not merely a technical label, it is a bridge between data and dreams, between what we can measure and what we long to find. In short, an Earth-like planet is a world that reflects the essential traits of our own, roughly Earth-sized, rocky in composition, and orbiting within a region that allows for liquid water. It may not be a perfect match, and it may conceal conditions that make it utterly hostile, but in the search for cosmic neighbors, it is the category that shines brightest. For every such world discovered, the possibility that Earth is not alone grows stronger. The definition, while imperfect, gives us a map of hope, a guide to where in the galaxy we should look when we ask the greatest question of all: are we alone? The concept of the habitable zone, often referred to as the Goldilocks zone, is central to the search for Earth-like planets. It is one of the most widely discussed ideas in astronomy because it sets the boundaries for where liquid water, a key ingredient for life as we know it, can exist on a planet's surface. The metaphor of Goldilocks comes from the children's story, where Goldilocks seeks porridge that is not too hot and not too cold, but just right. Similarly, a planet in the habitable zone must orbit its star at a distance that is neither too close nor too far away, but in the sweet spot where temperatures allow liquid water to remain stable. The habitable zone is not a fixed distance. It depends entirely on the type of star involved. Our Sun's habitable zone extends roughly from the orbit of Venus to just beyond Mars. Earth lies comfortably within this region, which is why our planet has oceans, rivers, and rain cycles. If Earth were a little closer to the Sun, our oceans would boil away, creating a runaway greenhouse effect similar to what we see on Venus. If Earth were a little farther, water would freeze into ice across the surface, making it a frozen world. Like Mars, that narrow strip of space is where life as we know it can thrive. And astronomers apply this same principle when they study other stars and their planets. Different stars create different habitable zones. A star much hotter and larger than the Sun will have its habitable zone located much farther out, since the radiation and heat are more intense. Conversely, smaller, cooler stars called red dwarfs have habitable zones much closer to their surface. This creates interesting challenges. For example, planets orbiting red dwarfs might be Earth-sized and located within the habitable zone, but because they orbit so close, they could be tidally locked. This means one side always faces the star in eternal daylight while the other side remains in endless night. The result could be extreme temperature contrasts that complicate the possibility of a stable, life-supporting environment. The idea of the habitable zone has been refined over the years. Early definitions were very simple: a range of distances where water could exist as a liquid. But planetary scientists now consider many additional factors: The composition of the planet's atmosphere, for instance, plays a huge role in determining surface conditions. A thick atmosphere with greenhouse gases can warm a planet significantly, expanding the habitable zone farther out. Conversely, a thin or absent atmosphere might shrink the habitable zone closer in. For example, Mars technically lies near the edge of the Sun's habitable zone, but its thin atmosphere prevents it from retaining heat, making the planet cold and dried out. The chemical makeup of a star can also affect the habitable zone. Stars with more heavy elements tend to produce planets with richer geology and possibly more complex atmospheres. Meanwhile, stars that are unstable, those that flare up with bursts of radiation, can make their habitable zones dangerous places. For life, this is particularly relevant with red dwarfs, which often release powerful stellar flares that could strip away the atmospheres of nearby planets. A planet could be in the right orbital position, but without protection from its star's violent activity, it may never maintain the conditions for habitability. Despite these complexities, the habitable zone remains a critical starting point. It gives astronomers a first filter when scanning thousands of exoplanets. If a planet lies within its star's habitable zone, it immediately becomes a subject of greater interest, warranting further investigation with more advanced tools. This is how some of the most famous exoplanet discoveries, such as the TRAPPIST-1 system and Kepler-4 have been highlighted. These worlds lie in or near habitable zones, making them prime candidates for further study. The habitable zone concept also stretches our imagination about where life could exist. While it is defined in terms of liquid water, some scientists point out that exotic forms of life might not need water at all. Could there be life in liquid methane or ammonia, as might exist on moons like Titan? If so, the habitable zone as we currently define it may be too narrow. But until we find examples of such alternative biochemistry, astronomers continue to rely on the model tied to liquid water, since it is the only confirmed solvent for life that we know. Another fascinating aspect of the habitable zone is how it evolves over time. Stars are not static, they grow, brighten, and change as they age. This means their habitable zones shift outward. Our Sun, for example, is slowly brightening over billions of years. As it does, the habitable zone creeps farther away. Earth, which now sits squarely within the zone, will one day be outside it. In roughly 1 billion years, the Sun's increased heat will boil Earth's oceans, rendering it uninhabitable. From this perspective, the habitable zone is not only about spatial location, but also about time, a moving target that shapes the window of opportunity for life. This temporal dimension carries profound implications for the search for extraterrestrial life. A planet may be in the habitable zone today, but was it habitable a billion years ago? Will it still be habitable in the future? The timing of conditions matters enormously. Life might take hundreds of millions of years to evolve, meaning that short windows in the habitable zone may not be enough. When astronomers evaluate Earth-like planets, they are not only asking if water could exist there now, but also whether the planet's history and future allow enough time for life to take root and flourish. In summary, the habitable zone is one of the most powerful tools in planetary science. It distills the vast complexity of the universe into a practical search criterion. Where can liquid water exist? While far from perfect, it has guided discoveries that continue to reshape our understanding of the cosmos. Each new planet found within a habitable zone becomes a spark of curiosity, a potential mirror to Earth, and a tantalizing candidate in our quest to answer the ultimate question of whether we are alone in the universe. When scientists talk about the possibility of life elsewhere in the universe, one phrase surfaces again and again: follow the water. This simple yet powerful directive is rooted in the idea that liquid water is the single most important ingredient for life as we know it. On Earth, every form of life, from the tiniest bacterium living in scalding volcanic vents to the largest blue whale in the oceans, depends on water in some form. It is the universal solvent, the medium in which the chemistry of life occurs. For this reason, when we search for Earth-like planets or assess the potential for habitability, water is the element we look for first. The importance of liquid water begins with chemistry. Life is fundamentally a complex network of chemical reactions and water provides the perfect environment for these reactions to occur. Its unique molecular structure gives it properties unlike any other liquid. Water molecules are polar, meaning they have a slight positive charge on one side and a negative charge on the other. This polarity allows water to dissolve a vast range of substances, from salts to organic molecules, making it the ideal medium for transporting nutrients and enabling the complex chemistry that underpins biology. Without such a solvent, it's difficult to imagine how molecules like proteins and DNA could assemble, interact, and replicate. On Earth, the relationship between water and life is inseparable. Every cell in every living organism contains water. In humans, about 60% of the body is made up of water, and blood largely water carries nutrients, oxygen, and waste products throughout our systems. Even extremophiles, the hardiest life forms on Earth, depend on water. These organisms live in boiling geysers, under crushing pressures deep in the ocean, or in the frozen tundra. Yet in each case, liquid water, even in trace amounts, is present. This provides a compelling argument. If life exists elsewhere, chances are high that it, too, will require water. This principle drives the focus of planetary exploration. When scientists explore our own solar system, their first priority is to search for evidence of past or present water. Mars, for example, has been a target of intense study because of signs that rivers, lakes, and perhaps even oceans once covered its surface. Even though much of Mars is now dry and barren, frozen water persists at its poles and beneath its soil. This keeps alive the possibility that microbial life may have existed or could still exist on the red planet. Similarly, moons like Europa, Enceladus, and Titan intrigue scientists because beneath their icy crusts lie vast oceans of liquid water, protected from the cold of space by thick ice shells and possibly warmed by geothermal activity. The presence of liquid water on exoplanets, planets orbiting stars beyond our solar system, is harder to prove directly. Astronomers cannot simply look through a telescope and see oceans glistening on a distant planet. Instead, they use indirect methods. By measuring the size of a planet, its distance from its star, and the star's energy output, scientists estimate whether conditions could allow liquid water to exist on the surface. If the planet lies in the habitable zone and is roughly Earth-sized, then the possibility of water is considered significant enough to warrant further study. However, water is not just about being present, it must also be stable. On Earth, the delicate balance of atmospheric pressure and temperature keeps water in liquid form. Across vast regions of the planet, too little atmospheric pressure and water evaporates into space, as happened on Mars. Too much heat and water vapor becomes trapped in the atmosphere, amplifying greenhouse effects and leading to runaway conditions, like on Venus, thus finding planets with the right conditions for stable, long-term liquid water is more complex than simply checking whether they are in the habitable zone. The search for water also shapes the instruments we design. The James Webb Space Telescope, JWST, for instance, is capable of analyzing the atmospheres of distant exoplanets, searching for signs of water vapor. If detected, this would be a groundbreaking confirmation of one of the critical ingredients for life. Closer to home, probes are being designed to drill into the icy crust of Europa or fly through the water plumes erupting from Enceladus, directly sampling potential habitats where life might exist. These missions highlight how central the search for water has become in our broader quest to find life. Despite this emphasis, scientists are careful to point out that life may not always require water. Some researchers speculate that other solvents, such as liquid methane or ammonia, could theoretically support life in exotic environments. Titan, Saturn's largest moon, is one of the prime candidates for such speculation. Its surface is covered with lakes and rivers of methane and ethane, raising the question of whether life could develop with chemistry very different from our own. But because water is the only solvent we know to support life, it remains the cornerstone of habitability studies. In other words, while alternative biochemistries are fascinating to consider, the scientific community prioritizes searching for water because it is the most promising and testable pathway. Water also plays a geological role. that contributes to habitability. On Earth, the water cycle regulates climate, shapes landscapes, and helps distribute energy across the planet. Rain erodes mountains, rivers carve valleys, and oceans stabilize global temperatures. Without these processes, Earth would not be the vibrant, dynamic environment it is today. Therefore, when scientists imagine Earth-like planets elsewhere, they envision not just stagnant pools of water, but dynamic cycles: clouds, rain, rivers, oceans interacting with geology and atmosphere to create a stable, life-supporting system. Finally, the presence of water ties deeply into humanity's hopes and imagination. To discover another world with oceans shimmering under alien suns would not only transform our understanding of life's potential, it would profoundly reshape our place in the cosmos. Water connects us, chemically and symbolically, to the possibility of companionship in an otherwise vast and silent universe. Each drop, whether on Earth or billions of light years away, is a reminder that life is not inevitable but precious, born in the delicate embrace of liquid water. In essence, the search for water is the search for life. Its presence signals possibility. Its absence suggests sterility. This is why astronomers, astrobiologists, and planetary scientists fix their gaze on the watery worlds, the planets and moons that hint at rivers, oceans, or subsurface seas. They are not simply looking for distant puddles, they are following the trail of life's most essential ingredient, a trail that could one day lead us to the discovery that we are not alone. The search for Earth-like planets took a monumental leap forward with the launch of NASA's Kepler Space Telescope in 2009. For the first time in history, humanity had a dedicated mission with a singular goal: to discover planets orbiting other stars. Before Kepler, only a few hundred exoplanets had been detected, most of them gas giants like Jupiter, found using ground-based telescopes. With Kepler, the universe suddenly became alive with new possibilities as the telescope revealed thousands of planets of all sizes and types, including many that were strikingly similar to Earth. The genius of Kepler lay in its method. Rather than attempting to capture images of distant planets directly, which remains a technological challenge even today, Kepler observed the brightness of over 150,000 stars continuously for years. It looked for tiny, periodic dips in brightness caused when a planet passed in front of its star. This method, called the transit method, is like noticing a brief flicker when a moth flies across a light bulb. From the depth and timing of these dips, astronomers could calculate the size of the planet and how long it took to orbit its star. In other words, Kepler could not only find planets, but also estimate whether they might lie in the habitable zone. The results were nothing short of revolutionary. Kepler discovered more than 2,600 confirmed exoplanets and identified thousands of additional candidates. These planets ranged from giant gas worlds to small, rocky bodies, and they orbited stars of every conceivable type. Suddenly, what had seemed rare, the idea of planets outside our solar system, was revealed to be commonplace. Nearly every star in the sky, it turned out, might host planets. Among the most exciting discoveries were planets that appeared to be Earth-sized and located in their stars' habitable zones. One famous example is Kepler 4b, often called Earth's cousin. This planet, about 1.6 times the size of Earth, orbits a star very similar to the Sun at nearly the same distance Earth does. It lies firmly within the habitable zone, sparking excitement that it could be one of the best candidates for life beyond our solar system. Although Kepler 4b is more than 400 light-years away, far beyond our reach, it represents the type of planet astronomers had dreamed of finding: rocky, Earth-sized, and bathed in the right amount of starlight. Another highlight was Kepler 186f, the first Earth-sized planet discovered in the habitable zone of another star. Smaller and cooler than our Sun, the star Kepler 186 is a red dwarf, and its planet Kepler 186f orbits close to it. Yet the planet still receives enough energy for liquid water to be possible on its surface. This discovery in 2014 made headlines around the world, not only because it proved that Earth-sized worlds in habitable zones exist, but also because it expanded the diversity of possible environments where life could thrive. Kepler also taught astronomers that planetary systems come in incredible variety. Some stars host tightly packed systems, with multiple Earth-sized planets orbiting closer than Mercury is to our Sun. Others have super-Earths, planets larger than Earth but smaller than Neptune, a category of world that does not exist in our solar system. These super-Earths might have thick atmospheres, shallow oceans, or volcanic activity unlike anything on Earth. Their discovery challenged scientists to broaden their definitions of what a habitable planet might look like. Perhaps the most profound insight from Kepler was statistical. By studying thousands of planets, astronomers could extrapolate to the galaxy as a whole. The data suggested that planets are more common than stars, and that Earth-sized planets in habitable zones are far from rare. Some estimates propose that there could be billions of potentially habitable worlds in the Milky Way alone. This realization shifted the conversation from "are there other planets like Earth?" to "how many are there, and which ones should we study first?" Yet Kepler's mission was not without its challenges. After several years, the telescope suffered mechanical failures in its gyroscopes, which were needed to keep it steady and pointed precisely at its star field. NASA ingeniously repurposed the spacecraft for the K2 mission, which extended its life by observing new patches of the sky with slightly reduced precision. Even in this diminished capacity, Kepler continued to make discoveries until its mission ended in 2018, when it finally ran out of fuel. By that time, it had transformed exoplanet science into one of the most dynamic fields of astronomy. Kepler's legacy is not only in the planets it discovered, but in the tools and missions it inspired. Its findings paved the way for the transiting Exoplanet Survey satellite TESS, launched in 2018, which is now scanning the nearest and brightest stars for planets. It also set the stage for the James Webb Space Telescope, which can study the atmospheres of promising exoplanets, searching for signs of water, oxygen, or other potential biosignatures. Kepler showed us where to look, and now newer instruments are delving deeper into those targets. The cultural impact of Kepler was also profound. Every time NASA announced a new Earth-sized planet in a habitable zone, the news made headlines across the world. People imagined alien landscapes, strange sunsets under unfamiliar skies, and the possibility that life might be thriving somewhere out there. For the public, Kepler transformed the search for life from a distant dream into a tangible scientific pursuit, rich with real data and real discoveries. In essence, the Kepler mission answered one of humanity's oldest questions: are planets like ours rare jewels, or are they common throughout the cosmos? Kepler's answer was clear: they are everywhere, and among them are many that could resemble Earth closely enough to raise the possibility of life. This revelation changed not only astronomy, but also our perspective on our place in the universe. No longer can we see Earth as uniquely special in terms of planetary formation. Instead, it is one of many worlds scattered across the galaxy that could harbor life. As we look forward, Kepler remains the telescope that opened the floodgates. It gave us the first real census of exoplanets and revealed a galaxy bursting with possibilities. Even though it now lies silent in space, its discoveries continue to shape our search for Earth-like worlds and ultimately for the answer to whether we are alone. Among all the planetary systems discovered so far, few have captured the imagination of scientists and the public quite like the TRAPPIST-1 system. Announced in 2017, this remarkable system, located about 40 light-years from Earth, contains 7 Earth-sized planets orbiting a single star. Even more astonishing, 3 of these planets lie within the habitable zone, where conditions could allow liquid water to exist. For the first time, astronomers had found not just a single Earth-like candidate, but an entire family of them in one place. TRAPPIST-1 is named after the telescope that first detected it. The Transiting Planets and Planetesimals Small Telescope TRAPPIST in Chile. Later, NASA's Spitzer Space Telescope and other observatories confirmed the discovery and added details. About the planets, the host star itself is a red dwarf, much smaller and cooler than our Sun. While our Sun is a yellow G-type star, TRAPPIST-1 is an ultra-cool M-dwarf, only about 9% the mass of the Sun and barely larger than Jupiter. Its small size and dim light mean that its habitable zone is extremely close in, so its planets orbit in tight, compact orbits. What makes TRAPPIST-1 extraordinary is the sheer number of Earth-sized worlds packed into such a small space. All 7 planets are between 0.76 and 1.13 times the size of Earth, making them strikingly similar in scale. They orbit their star at distances so close that the entire system could fit within the orbit of Mercury around our Sun. Despite this compactness, their arrangement is stable, and they even exhibit orbital resonances, where the gravitational tugs between them create rhythmic patterns of motion. This resonance suggests the planets formed further out and migrated inward together, maintaining their delicate balance. The 3 most intriguing planets are TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. These lie within or near the habitable zone, receiving just the right amount of starlight for liquid water to be possible on their surfaces. TRAPPIST-1e, in particular, is considered one of the most promising Earth-like exoplanets ever found. It is nearly the same size as Earth, has a density suggesting a rocky composition, and receives about the same amount of stellar energy as our planet does from the Sun. If any world beyond our solar system could resemble Earth, TRAPPIST-1e may be it. However, the TRAPPIST-1 system also presents challenges because the star is a red dwarf. Its planets orbit much closer than Earth orbits the Sun. This raises the likelihood that the planets are tidally locked, meaning one side always faces the star while the other remains in permanent darkness. Such conditions could create extreme temperature differences, potentially freezing the dark side while boiling the day side. Yet, if the planets have thick atmospheres or oceans, heat might be redistributed around the globe, creating habitable conditions. Despite the tidal locking. Another concern is stellar activity. Red dwarfs are notorious for producing powerful solar flares and bursts of radiation. These flares could strip away the atmospheres of nearby planets, leaving them barren and unprotected. Scientists are actively studying TRAPPIST-1 to determine whether its planets can hold onto their atmospheres despite such activity. If they can, then these worlds may offer some of the best opportunities for life beyond Earth. The excitement around TRAPPIST-1 is not just theoretical. The system is close enough that current and upcoming telescopes can study it in detail. The James Webb Space Telescope, JWST, launched in 2021, has made TRAPPIST-1 one of its top priorities. With its ability to analyze the atmospheres of exoplanets, JWST can look for water vapor, carbon dioxide, methane, or even potential biosignatures. For the first time, scientists may be able to directly assess the habitability of planets beyond our solar system, and TRAPPIST-1 is at the center of that effort. The discovery of TRAPPIST-1 also reshaped how we think about planetary systems. Before, we imagined systems like ours, with a mix of rocky inner planets and gas giants farther out. TRAPPIST-1, by contrast, shows that tightly packed systems of Earth-sized planets around small stars may be common. In fact, red dwarfs make up about 70% of the stars in our galaxy. If systems like TRAPPIST-1 are typical, then the number of potentially habitable planets in the Milky Way could be staggeringly high. Beyond its scientific significance, TRAPPIST-1 has ignited the human imagination. Artists and filmmakers have depicted the view from its planet's skies, filled with multiple neighboring worlds hanging large and bright, far closer than our moon appears from Earth. Standing on TRAPPIST-1f, for instance, one might look up and see another Earth-sized planet looming in the sky, its features visible without a telescope. Such vistas remind us of how varied and wondrous the universe could be. Philosophically, the TRAPPIST-1 system raises profound questions. If 3 planets in one system are potentially habitable, what does that mean for the odds of life elsewhere? Are we on the brink of discovering that the galaxy teems with living worlds? Or will TRAPPIST-1's planets turn out to be sterile, reminding us that habitability is more fragile than it appears? Either outcome will transform our understanding of life in the cosmos. In conclusion, the TRAPPIST-1 system is one of the crown jewels of exoplanet discovery. With 7 Earth-sized worlds, 3 of them in the habitable zone, it offers perhaps the best laboratory yet for studying habitability beyond our solar system. Its proximity allows unprecedented observational opportunities, and its diversity provides insights into planetary formation and survival around small stars. Whether these worlds are barren or alive, the TRAPPIST-1 system has already changed the course of astronomy. It stands as a beacon of possibility, showing us that entire families of Earth-like worlds may be waiting just beyond our reach. When we talk about the habitability of Earth-like planets, one factor above all others determines whether life can truly take hold: the atmosphere. An atmosphere is not just a blanket of gases, it is a shield, a regulator, and a cradle for life. On Earth, our atmosphere protects us from harmful solar radiation, traps enough heat to maintain liquid water, and provides the very oxygen we breathe. For exoplanets, the presence and nature of an atmosphere may be the decisive line between a barren rock and a living world. To understand why an atmosphere is so essential, consider Mars and Venus, two planets in our own solar system often compared to Earth. Mars is small, and over billions of years it lost most of its atmosphere. Without that shield, solar radiation bombards its surface, and whatever water it once had is now locked as ice or evaporated into space. Venus, by contrast, has an atmosphere that is far too thick, made mostly of carbon dioxide. It traps heat in a runaway greenhouse effect, pushing surface temperatures to more than 450 C, hot enough to melt lead. Earth sits in the delicate balance between these two extremes, with an atmosphere that is just right. When astronomers search for Earth-like planets, they know that atmosphere is the key. The discovery of a planet in the habitable zone is only the first step. If that planet lacks an atmosphere, it will likely be sterile. If it has the wrong kind of atmosphere, too thin, too thick, or toxic, it may not support life as we know it. Thus, detecting and analyzing exoplanet atmospheres has become one of the most exciting frontiers in modern astronomy. The James Webb Space Telescope, JWST, represents a game-changing leap in this effort. For the first time, scientists have the tools to peer into the atmospheres of small, rocky exoplanets. By observing starlight that passes through a planet's atmosphere during transit, JWST can reveal the chemical fingerprints of gases like water vapor, methane, oxygen, and carbon dioxide. Each of these gases tells a story. Water vapor suggests the possibility of oceans or lakes. Methane, if not produced by volcanism, might be a byproduct of life. Oxygen, on Earth, is largely produced by plants and microorganisms. Finding it elsewhere could be a strong biosignature. Of course, not all atmospheres are equal when it comes to sustaining life. A promising Earth-like planet would need an atmosphere thick enough to retain heat and protect against harmful radiation, but not so thick as to suffocate the surface. It would also need a mix of gases compatible with life, perhaps nitrogen as a background gas, carbon dioxide in small amounts to regulate temperature, and ideally oxygen for complex life. Detecting such a balanced composition is no easy task, but even partial clues can push us closer to understanding which planets are truly habitable. Red dwarf systems like TRAPPIST-1 highlight both the promise and the challenge of atmospheric studies. On one hand, the planets are so close to their dim star that they are easier to observe. On the other hand, red dwarfs frequently release strong stellar flares that could strip atmospheres away. If TRAPPIST-1's planets manage to hold onto their atmospheres despite these flares, it would be an encouraging sign that habitable conditions can persist even around volatile stars. Another fascinating possibility is the presence of exotic atmospheres unlike anything we see on Earth. Some exoplanets may have thick hydrogen-rich atmospheres, while others could be dominated by carbon monoxide, ammonia, or sulfur compounds. While these might not support human life, they raise the question of whether alien forms of life could thrive under conditions vastly different from our own. Our search for life should be broad, open to the idea that life elsewhere might adapt to environments we would consider hostile. But even as we expand our imagination, scientists remain cautious. A biosignature like methane or oxygen could, in principle, be produced by non-living processes. For example, methane can arise from volcanic activity, while oxygen can accumulate when ultraviolet light breaks apart water vapor. The challenge is distinguishing biological signals from geological or chemical ones. This means that finding a single gas is not enough. Astronomers will look for combinations of gases that together suggest biological activity. On Earth, for instance, the coexistence of oxygen and methane in the atmosphere is only possible because life constantly replenishes both gases. Without life, they would quickly react and vanish. The detection of a life-supporting atmosphere on an exoplanet would be a historic moment in science, but it would also raise deeper philosophical questions. If we find a planet with an atmosphere like Earth's, rich in water vapor, oxygen, and traces of methane, do we assume life is there, or will we need even stronger evidence, like seasonal variations in gases that suggest biological cycles? The search for life in atmospheres is not only about finding habitable conditions, but also about testing the very limits of our ability to recognize life from afar. Atmospheres are also important in shaping the long-term stability of life. A planet might be habitable today, but may have been too harsh in the past, or could become inhospitable in the future. By studying atmospheric evolution, scientists can learn whether planets have stable climates over billions of years, the kind of stability life likely requires to flourish. Earth's atmosphere, for example, has changed dramatically over time, from a carbon dioxide-heavy early atmosphere to the oxygen-rich one we know today. Thanks to the emergence of photosynthetic life, could similar transformations be happening on distant planets? Ultimately, the study of exoplanet atmospheres represents a bridge between astronomy and biology. It is where the question of "is this planet Earth-like?" transforms into "could this planet be alive?" Each new observation brings us closer to answering one of humanity's oldest questions. Are we alone in the universe? The answer may well come not from images of alien landscapes or signals from intelligent beings, but from the faint signatures of gases in a distant atmosphere, whispering across the cosmos that life has taken hold on another world. The discovery of Earth-like planets relies on some of the most ingenious methods humans have ever devised to study the universe. We cannot simply point a telescope and take a photograph of these distant worlds. They are too small, too dim, and too close to their dazzling host stars. Instead, astronomers must use indirect methods detecting the tiny effects that planets have on their stars to infer their presence. Over the last few decades, these techniques have transformed astronomy, leading to the detection of thousands of exoplanets and opening a window to entire planetary systems beyond our own. One of the most powerful and widely used methods is the transit method. Imagine a planet crossing in front of its star from our perspective here on Earth. As it does, the star's light dips ever so slightly, creating a repeating pattern of dimming and brightening. This is a transit. By measuring these dips with incredible precision, astronomers can determine a planet's size, orbital period, and sometimes even hints about its atmosphere. NASA's Kepler Space Telescope revolutionized exoplanet discovery. By using this method, over its mission, Kepler identified more than 2,600 confirmed exoplanets, many of them Earth-sized and located in the habitable zones of their stars. The beauty of the transit method is that it can provide a wealth of information from a seemingly tiny signal. For instance, the depth of the dip reveals the planet's radius. The interval between dips shows its orbital period, which, combined with the star's characteristics, gives us the planet's distance from its star. Even more astonishing, during a transit, a fraction of starlight filters through the planet's atmosphere. By analyzing this light with instruments like the James Webb Space Telescope, astronomers can detect the fingerprints of atmospheric gases, water vapor, methane, oxygen, and more. However, the transit method has its limitations. It only works if the planet's orbit happens to align in such a way that it passes directly between us and its star. Many planetary systems are tilted at angles that prevent us from seeing such transits. For every planet we do detect, there may be dozens more that remain hidden simply because their geometry is wrong. From our perspective, to complement the transit method, astronomers use the radial velocity method, also known as the Doppler wobble technique. Stars do not remain perfectly still as planets orbit them. Instead, the gravitational pull of a planet causes it start to wobble slightly, moving toward and away from us in a repeating cycle. This motion shifts the star's light spectrum toward the blue when it moves closer and toward the red when it moves away. By carefully measuring these shifts, astronomers can detect the presence of planets, even if they never transit. The radial velocity method was the very first technique that revealed exoplanets. With the discovery of 51 Pegasi b in 1995, a gas giant orbiting close to its star. Since then, the method has been refined to extraordinary precision. Today, radial velocity measurements can detect planets only a few times the mass of Earth, providing vital data on their masses. When combined with the radius from transits, this allows scientists to determine density and thus infer whether a planet is rocky like Earth, gaseous like Neptune, or something in between. A third, less common but growing technique is direct imaging. As the name suggests, this involves actually capturing a picture of an exoplanet. This is extremely difficult because stars outshine their planets by millions of times. To succeed, astronomers use special instruments like coronagraphs, which block out starlight, or even space-based starshades, giant structures that fly in formation with telescopes, to create artificial eclipses. Direct imaging has so far revealed mostly large, young, and hot planets orbiting far from their stars, glowing in infrared light, while not yet suitable for Earth-sized planets. Advancements in technology may one day allow us to directly photograph a pale blue dot around another star. Another intriguing method is gravitational microlensing. According to Einstein's theory of general relativity, massive objects bend light. When a star with a planet passes in front of a more distant star, the gravity of the nearer system magnifies the light of the background star. If a planet is present, it adds a distinctive signature to the lensing effect. This method does not require transits or wobbles and can detect planets that would otherwise remain invisible. Microlensing is particularly good at finding planets far from their stars, or even rogue planets drifting alone in space. Additionally, astronomers are experimenting with astrometry, which measures the precise position of a star in the sky and looks for subtle shifts caused by orbiting planets. This method is difficult from Earth due to atmospheric distortion, but may become more effective with advanced space telescopes. Each detection method has strengths and weaknesses, and together they form a complementary toolkit. Transits give us size, radial velocity gives us mass, direct imaging gives us visuals, and microlensing expands the range of detection. By combining these approaches, astronomers can build a fuller picture of distant planets, turning points of light into worlds with measurable properties. The TRAPPIST-1 system is an excellent case study in how these methods work together. Initially, its planets were discovered through transit dips in brightness. Radial velocity measurements then refined their masses. Future observations with JWST aim to probe their atmospheres during transits. The synergy of methods turns discovery into characterization, helping us not only detect planets, but also evaluate their habitability. Looking ahead, detection techniques will only become more advanced. Next-generation telescopes like the extremely large telescope Elton Chile or future space missions like LAVOIR and HABEX may push the limits even further. These instruments could make direct imaging of Earth-like planets possible, revealing continents, oceans, or seasonal changes in their atmospheres. The methods that began with faint wobbles and tiny dips may one day deliver something profound, a view of another living world. The role of advanced telescopes in the search for Earth-like planets cannot be overstated. If early ground-based telescopes were like primitive glasses, through which astronomers first glimpsed faint signals of other worlds, today's instruments are more like interstellar microscopes, capable of dissecting the light from distant stars to reveal the hidden fingerprints of planets orbiting them. Each generation of telescopes builds upon the last, pushing the boundaries of sensitivity, precision, and resolution, transforming what was once speculative into tangible science. One of the most revolutionary instruments to date is the James Webb Space Telescope, JWST, launched in late 2021. JWST was designed not primarily as a planet-hunting telescope, but its infrared capabilities have turned it into a powerhouse for exoplanet science. Infrared light is essential for studying planetary atmospheres, as many important molecules, water vapor, methane, carbon dioxide, leave distinct absorption patterns in this part of the spectrum. When a planet passes in front of its star, a sliver of starlight filters through its atmosphere, carrying with it the chemical signatures of gases. JWST's instruments, like NIRSPEC and MIRI, are capable of analyzing this starlight in exquisite detail, potentially allowing astronomers to detect biosignature gases on rocky exoplanets. The TRAPPIST-1 system, with its 7 Earth-sized planets, has been a particular target for JWST. Some of these planets orbit within the star's habitable zone, making them prime candidates for atmospheric studies. For the first time in history, we may soon have evidence not only of a rocky world in a habitable zone, but also whether it possesses water vapor or protective atmospheres, critical ingredients for life. Although JWST's schedule is crowded and competition for observation time is fierce, each dataset adds an invaluable piece to the puzzle of whether life might exist beyond Earth. But JWST is only the beginning. On Earth, an entire generation of extremely large telescopes is under construction, promising to take exoplanet science to unprecedented levels. Among them is the European Southern Observatory's extremely large telescope ELT in Chile, with a staggering 39-meter main mirror, by far the largest optical telescope ever built. The ELT will collect more light than any telescope in history. This immense power will allow astronomers to directly image smaller exoplanets and even analyze the reflected light from Earth-sized worlds around nearby stars. Another contender is the 30-meter telescope TNT, planned for Hawaii or an alternative site with adaptive optics to correct for atmospheric turbulence. The TNT will achieve incredible resolution, enabling detailed studies of exoplanet atmospheres and surfaces. Similarly, the giant Magellan Telescope GMT in Chile, constructed from 7 massive mirror segments, will rival the ELT in capabilities. Together, these observatories will serve as ground-based counterparts to JWST, offering complementary data and flexibility that space telescopes alone cannot provide. Beyond current projects, ambitious proposals like LAVOIR, Large UV Optical, Infrared, Surveyor, and HABEX, Habitable Exoplanet Observatory, represent the long-term future of exoplanet exploration. These next-generation space missions, still in conceptual stages, aim to go beyond detection and into direct characterization. They would employ advanced coronagraphs or even deploy Starshade's giant, flower-shaped shields flying thousands of kilometers away from the telescope to block out starlight. With these techniques, LAVOIR or HABEX could directly image Earth-like planets in reflected light, perhaps even revealing oceans, continents, and seasonal weather patterns. Imagine what such a breakthrough would mean. For the first time, we might see a pale blue dot orbiting another sun, its light split into spectra showing oxygen, ozone, water vapor, and perhaps methane, all together suggesting a biosphere at work. These telescopes would shift the question from do Earth-like planets exist, which we already know, to do any of them host life. In addition to their technical capabilities, advanced telescopes serve another crucial role. They inspire global collaboration. Projects like the ELT and JWST involve dozens of countries, hundreds of institutions, and thousands of scientists and engineers. The search for Earth-like planets is no longer the pursuit of isolated observatories. It has become a worldwide effort, uniting expertise and resources from across the globe. Moreover, the rapid progress of telescope technology reflects a broader theme in human history: the relentless drive to see further, to understand more, and to push the boundaries of the unknown. Just as Galileo's telescope once shattered the illusion of a perfect, Earth-centered universe, JWST and its successors may one day shatter the illusion that Earth is unique in hosting life. However, even these marvels face challenges. Time allocation on JWST is limited. Weather can interrupt ground-based observations, and the sheer complexity of instruments like the ELT makes them vulnerable to delays. Yet the progress is undeniable. Every new telescope sharpens our vision of the cosmos, turning faint whispers of data into coherent narratives of alien worlds. In the coming decades, These instruments may deliver the most profound discovery in human history, evidence of life beyond Earth, whether it comes as a faint spectral signature of oxygen, a surprising imbalance of gases, or even a direct image of a planet with cloud patterns resembling our own. The role of telescopes will be central. They are our eyes into the vastness, our tools for transforming curiosity into knowledge. It is entirely possible that somewhere, orbiting a quiet star in a familiar spiral arm of the Milky Way, there is a planet very much like our own. And thanks to telescopes like JWST, the ELT, and those yet to come, we may not only discover it, we may come to know it intimately, as a distant twin to Earth and a reminder that our world is not alone. For all the breathtaking progress in finding planets beyond our solar system, the quest to confirm a true Earth twin remains a formidable challenge. The phrase itself, Earth twin, implies not just another rocky planet of similar size and mass, but one that also shares the defining conditions of our world: a stable atmosphere, liquid water, and perhaps even a biosphere. Yet as telescopes gather more data and detection methods become more sophisticated, astronomers are increasingly aware of how tricky it is to move from Earth-like in some respects to truly Earth-like in every critical way. One of the primary difficulties lies in defining habitability itself. While scientists often use the concept of the habitable zone, the range of orbital distances where liquid water could exist, this is a blunt tool. A planet can orbit in the habitable zone and still be utterly inhospitable. Venus is a perfect example. It orbits near the inner edge of the Sun's habitable zone, is nearly identical to Earth in size, yet its thick carbon dioxide atmosphere and runaway greenhouse effect have turned it into a blistering wasteland with surface temperatures hot enough to melt lead. Conversely, moons like Europa or Enceladus orbit far outside the traditional habitable zone, yet may harbor liquid oceans beneath icy crusts due to internal heating. So while the habitable zone is a useful filter, it doesn't guarantee Earth-like conditions. Another barrier is the limitation of current detection methods. Transit photometry can reveal a planet's size, orbital period, and sometimes atmospheric signatures, but it cannot easily tell us about surface conditions or geology. Radial velocity methods provide estimates of mass, but not precise composition. Direct imaging is extremely difficult because Earth-sized planets are tiny specks of light, lost in the overwhelming glare of their parent stars. Even with state-of-the-art instruments like the James Webb Space Telescope, astronomers can only gather fragmentary clues about atmospheres, and those clues are often noisy, ambiguous, or incomplete. Confirming that an exoplanet has oceans or continents is far beyond current capabilities. Then comes the issue of false positives in biosignatures. Scientists often highlight oxygen, methane, or ozone as potential signs of life because, on Earth, they are strongly linked to biological activity. However, these gases can also rise from purely abiotic processes. For instance, photochemical reactions in certain atmospheres could generate oxygen without any life at all. Methane can be released by volcanic processes. This means that detecting one of these gases alone is not enough. Researchers must find specific combinations and contextual evidence to build a strong case for biology. Until we can collect more complete spectra or resolve finer details of planetary atmospheres, confirming life will remain speculative. Even if atmospheric signatures suggest habitability, there's the challenge of planetary environments being dynamic and changeable. Planets are not static. Climates can swing dramatically over time. Earth itself has gone through snowball Earth phases where nearly the entire surface was frozen, and greenhouse periods when tropical climates stretched almost to the poles. A snapshot of an exoplanet might catch it in a phase that appears habitable or uninhabitable, but without long-term observation, we cannot know how stable its climate really is. Adding to the difficulty is the role of stellar activity. Many of the most promising exoplanets orbit red dwarfs, stars that are smaller and cooler than the Sun. These stars are abundant and long-lived, making them attractive targets for habitability studies. However, they are also prone to intense flares and radiation bursts that could strip atmospheres or sterilize surfaces. A planet in the habitable zone of a red dwarf might be blasted regularly with ultraviolet or X-ray radiation, making it far less Earth-like than its orbital position suggests. Determining whether such planets can hold onto atmospheres is one of the toughest challenges astronomers face, even when the data suggest a world that is tantalizingly similar to Earth. There's the problem of distance. The nearest potentially habitable planets, such as those around Proxima Centauri or in the TRAPPIST-1 system, are still light years away. At present, we can observe them only as faint blips of light. To truly confirm habitability or detect direct evidence of life, we would need missions capable of interstellar travel or at least robotic probes, able to cross such distances, technologies that remain in the realm of long-term speculation. For now, astronomers must work with remote sensing, which is inherently limited. There is also a philosophical and cultural challenge. The idea of an Earth twin implies a level of similarity that may not even exist. Life on Earth is deeply adapted to this planet's unique circumstances, and it's possible that elsewhere, life could thrive under very different conditions. By searching too narrowly for Earth copies, we may miss entirely different forms of habitability. In this sense, the challenge is not only technological but conceptual. How do we recognize life as we don't know it when we see it? Despite these obstacles, astronomers are optimistic. Each challenge is also an opportunity for innovation. For example, improving models of planetary atmospheres can help distinguish false positives in biosignatures. Developing more sensitive instruments can push the boundaries of detection, and international collaboration ensures that multiple methods, perspectives, and data sources are combined to reduce uncertainties. Ultimately, the challenge of confirming a true Earth twin reminds us of the complexity of the cosmos and the humility required to study it. Earth is not simply a rocky world at the right distance from its star. It is the product of countless interwoven factors: plate tectonics recycling carbon, a protective magnetic field shielding the surface, a large moon stabilizing axial tilt, and a rich history of biological coevolution shaping the atmosphere. Replicating this full suite of conditions elsewhere is a high bar indeed. Yet the difficulty of the task is what makes the pursuit so thrilling. Every limitation sparks new questions. What if habitable worlds are rare? What if life is common, but rarely produces detectable signatures? What if Earth-like planets exist in abundance, but we are only at the dawn of developing the technology to recognize them? These questions propel science forward, reminding us that the search is as much about refining our understanding of life itself as it is about cataloging distant planets. In the end, the struggle to confirm true Earth twins highlights a paradox. The more we discover, the more we realize how much we do not yet know, and perhaps that is fitting. After all, Earth's uniqueness is what gives our search meaning. The dream of finding another Earth, however elusive, drives innovation, curiosity, and a sense of shared destiny among humanity. Even if the first true Earth twin remains unconfirmed for decades, the journey itself will reshape our vision of the universe and our place within it. The search for Earth-like planets does not exist solely within the domain of science and technology. It resonates deeply with human imagination, philosophy, and culture. For thousands of years, people have looked to the stars and wondered whether other worlds, like our own, might exist. Each discovery of a new exoplanet revives ancient questions about identity, meaning, and our place in the universe. The possibility of finding a true Earth twin is not just a scientific milestone. It is a cultural and philosophical turning point that reshapes how we understand ourselves. One of the most profound implications lies in the shift of perspective it forces upon humanity. Throughout history, paradigm-shifting discoveries have repeatedly displaced Earth from the center of cosmic importance. Copernicus showed that Earth orbits the Sun. Darwin revealed that humans are part of the evolutionary fabric of life rather than separate from it. The discovery of other Earth-like planets would continue this trend, underscoring that our world may not be singular. If other habitable planets exist, then Earth is not the exception, but part of a vast cosmic continuum. Such a realization could humble us and, at the same time, inspire awe at being part of something far larger than ourselves. For many, this search also connects directly to questions of existence and purpose. If Earth-like planets are common, then the chances that life or even intelligent life exists elsewhere increase dramatically. This raises profound questions. Are we alone? If not, how should we view ourselves in relation to potential extraterrestrial civilizations? Philosophers, theologians, and artists alike grapple with these ideas, each offering different interpretations. Some argue that discovering another inhabited world would diminish humanity's uniqueness. Others see it as expanding the circle of kinship beyond Earth. Even in the absence of confirmed alien life, the search has practical cultural consequences. Knowing that Earth is not the only potentially habitable planet may influence how we treat our own. Awareness of other worlds, both fragile and enduring, underscores the fragility of Earth's ecosystems. It can serve as a mirror, reminding us that while planets may be numerous, each one is unique, shaped by delicate balances that are easily disturbed. This perspective could foster a greater sense of environmental stewardship, motivating humanity to protect the only habitable planet we currently know for certain, our own. Another dimension is the dream of exploration and migration. Throughout human history, frontiers have symbolized opportunity and survival. The idea that other Earth-like planets might one day be reachable ignites the imagination, fueling visions of interstellar travel and new homes for humanity. While such journeys remain far beyond our technological capabilities, they inspire both science fiction and real scientific inquiry. Cultural narratives of migration, adventure, and survival are projected onto the stars, offering humanity both hope and a long-term vision of continuity beyond Earth. There's also a philosophical caution embedded in the search. The discovery of Earth-like planets might encourage us to imagine escape routes from ecological collapse or overpopulation. Yet relying on distant, hypothetical worlds as backups could foster complacency about caring for Earth. In truth, even if habitable planets exist, reaching them may be impossible for centuries, if not millennia. Thus, the real value of these discoveries lies not in finding replacements, but in reminding us that our home is precious and must be safeguarded. Culturally, the search for Earth twins sparks a renaissance of storytelling and creativity. Literature, cinema, and art are deeply influenced by scientific discoveries. Films like Interstellar, novels like The Three-Body Problem, and countless works of speculative fiction draw inspiration from the possibility of other habitable worlds. These cultural works, in turn, feed back into public interest, creating a cycle where science inspires art, and art inspires the next generation of scientists. The pursuit of Earth-like planets thus becomes not only a scientific endeavor, but also a shared cultural story that transcends disciplines and borders. On a more intimate level, contemplating other Earths has existential and emotional effects. It reminds individuals of both the vastness of the cosmos and the smallness of human life. For some, this induces a sense of insignificance. For others, it generates a feeling of connection. If life exists elsewhere, then life is a cosmic phenomenon, not confined to our little corner of the universe. This duality between humility and belonging mirrors the way the night sky has always inspired both awe and reflection. There are also ethical dimensions to consider. If one day humanity gains the ability to travel to other Earth-like planets, questions of colonization, preservation, and contact will arise. Should we settle new worlds if they are pristine? What responsibilities would we have if those planets harbor life, even in microbial form? These ethical questions must be anticipated long before they become practical realities. The way we answer them will shape not just our future in space, but our moral identity as a species. Finally, the search for Earth twins reinforces a powerful sense of unity on Earth itself. When astronomers speak of another Earth, they remind us that all humanity shares this one fragile planet. Borders, conflicts, and divisions fade in significance compared to the shared challenge of protecting and understanding our home. Just as the Apollo missions famously gave us the Earthrise image that changed how people saw their planet, the discovery of an Earth-like twin might serve as a new symbol of global perspective, encouraging cooperation across nations in the pursuit of knowledge and survival. In the end, the philosophical and cultural implications of Earth-like planets are as vast as the stars themselves. The search transcends science It is a mirror that reflects human curiosity, creativity, and longing. Whether or not we ever confirm another true Earth, the act of searching changes us. It broadens our horizons, deepens our sense of wonder, and challenges us to imagine futures that stretch far beyond the confines of our planet. The journey toward finding Earth's twin is, at its heart, a journey of self-discovery, reminding us that to understand the cosmos is also to better understand ourselves. Every Earth-like planet discovered is a reminder that the universe may be teeming with worlds and perhaps civilizations waiting to be found. So, do you believe there's another Earth out there with life? Share your thoughts in the comments. And don't forget to like and subscribe for more journeys through the cosmos.